Welcome back, everybody. It's great to have with me the one and only Quantum Kessler, Eric Kessler from AWS. So he'll be speaking to us today about all the wonderful things on Braket and PennyLane. Eric does have a background in quantum. He has a PhD from the Max Planck Institute for Quantum Optics. Unfortunately, after that, he got seduced by the glitter and glitz of the AI and ML world, where he spent 5 years working for giants like IBM and AWS. But thankfully, we got him back now on the quantum side with his role as Senior Product Manager of Science for Amazon Braket at AWS. So with that, I'll pass it off to Eric.
Awesome. Thank you, Rafael. And thanks so much for giving me the opportunity to speak here. It's a super exciting event. I've been following the talks, and I'm super curious about the hackathon and everything that's going to come in the next week. So yeah, thanks a lot, and I'm excited to go through this. I wanted to take the next 30 minutes to tell everybody a little bit about a couple of things in terms of how we see quantum computing at AWS, specifically around Amazon Braket, but then also how we think about the combination of machine learning and quantum computing, and what AWS and Braket together with PennyLane are planning to do. And finally, as probably many of you have heard, AWS is sponsoring the second week of this event, where we have the Open Hackathon with AWS credits. And I'm going to give you a couple of tips and tricks how to get started, what best practices are, and walk you through the timeline there. Okay, but first, I wanted to make a step back. So I assume many of you have heard about Amazon Braket, which is our quantum computing service that we launched in preview in December of 2019, and then we went generally available in August of last year. This is our way of trying to bring quantum computing to more people. Essentially, everybody with an AWS account can access quantum computers on Amazon Braket since August of last year. But that was only one part of our strategy in quantum computing at AWS. Concurrently with Amazon Braket, we launched two other pillars in quantum computing. The first one being what we call the Amazon Quantum Solutions Lab, which is our research team that works together with customers on research projects around quantum computing, but also adjacent fields, right? Like everything at AWS, we want to work backwards from the customer problem, meaning we want to look around the corner and see what we can do today already with HPC, machine learning, and other tools on AWS, but also, of course, what will become relevant in the future in terms of quantum computing and doing deep research along those lines. And then the other thing that we launched at that time is the AWS Center for Quantum Computing. This is super exciting. It's a research center on the campus of Caltech, where our goal is really to push the boundaries in terms of quantum computing research, in algorithms, in error correction, but also looking into the development of quantum computing hardware. So the Center for Quantum Computing is run by Oscar Painter on the experimental side and Fernando Brandao on the theoretical side. And we have a lot of fantastic people that have joined us since we launched the center. So it's super exciting to have everybody on board. That is probably, though, a deep dive for another day. And I want to focus now on Amazon Braket. So as I said, Amazon Braket is a fully managed AWS service that with the goal to make it easy for everybody with an AWS account to start experimenting with quantum computing. The way we think about Braket is really in these three modules around build, test, and run. So in the first module, we provide managed development environments in the form of Jupyter environments that come pre-installed with different software tools that you need to build your algorithms, for example, PennyLane. And then in the second module, we provide managed circuit simulators and a local simulator that help you test your algorithm, run your circuits, essentially send them to an API and get the results back to help you accelerate your workflow in algorithm development. And then, of course, most importantly, we also provide secure and on-demand access to quantum computing hardware. And of course, we want to make the transition between test and run as smooth as possible. As we all know, this is not a linear cycle here, right? So you jump back and forth between these modules. And in the ideal case, you would just change a single line of code to go from a simulator onto a quantum computing hardware. Yeah. So today, we have 3 different types of quantum computing technology available on Braket. That is a quantum annealer from D-Wave. We have a trapped ion quantum computer from IonQ, and we have superconducting chip-based machines from Rigetti. And for me, most excitingly, right, all of these things are available today on AWS. So everybody with an AWS account, you can just create an account today. You can log in, you see these devices, and you can run against them. We have an on-demand pricing model, so there's 0 upfront commitment. You can just log in and get started. It was also very important for us that, all of this, we don't consider quantum computing as this orthogonal thing to AWS, right? So in that spirit, everything that we build with Amazon Braket is deeply integrated into the AWS platform, into their ecosystem, for example, for user access management, for monitoring, for logging and security, etc., right? So we really want to make sure that that we're not living in our own bubble, but having quantum computing be one of the tools that our customers can access on AWS. So after this quick intro, I do want to switch gears and start talking about, learning quantum machines or variational algorithms or whatever you want to call it, and what we're doing together with PennyLane to give you a little bit of an insight how we're looking at that space at the intersection of machine learning and quantum computing. And I'm gonna start at a point where you're probably gonna roll your eyes at this point after the 3rd day into the conference. And I don't want to bore you, but stay with me here for a moment. It will make sense, the point that I'm trying to drive here. So obviously we're all here for, because of the promise of large-scale quantum computing, right? We know that we have these holy grail algorithms that promise to be really transformational in a broad area of different fields, from chemistry to materials science, optimization, and so on and so forth. We also know that these algorithms require error correction at a large scale, which is probably deep in the future. Yeah, so we don't expect that to show up within the next couple of days. So, and the question obviously is, what do we do until then? And I bet you have heard a lot of talks at this point about the big idea about variational quantum computing or hybrid quantum computing that is really based on on algorithms, on heuristic algorithms, where you provide a ansatz, a circuit class essentially, and then have a classical computer optimize within the boundaries of that circuit class to find the best circuit for your problem. So you actually don't program the circuits directly, but you have an algorithm, a classical algorithm that finds that optimal circuit or near optimal circuit iteratively in an optimization loop. And we talked a lot about these algorithms, but I do want to make the point that within these 2 slides, this is such an shift in mindset, a shift in paradigm that is hard to overstate, right? So when you think back, when these other algorithms, the fault-tolerant algorithms were developed in the time, perhaps a decade ago, the field of quantum computing was almost exclusively focused on theoretical proofs, on complexity theoretical arguments. What are really the scaling behavior of these algorithms? What is the computational complexity that you can address? Prefactors were not all that relevant, and there were only a couple. Still today, we only have a handful of these algorithms available. And contrast that with the point where we are today with quantum computing, right? So in this field of variational quantum computing, we know next to nothing about these algorithms, right? So the theoretical understanding of what is the complexity or the computational power of these algorithms is quite nascent. We don't know all that much about it, and in many cases, the answer to the question, what can we do with it, will be, well, we have to build a device and we have to find it out. So this is a huge shift in mindset, and a big change that the quantum computing community is undergoing, and has been undergoing over the last couple of years. And that's a point I wanted to make, because it is not a paradigm shift that is unseen or unheard of, right? There's another field that went through the same evolution. When you think back in machine learning, where we are today with quantum computing, this is very similar to where machine learning was perhaps two decades ago, right? I mean, you can just look at the algorithms, right? It's exactly the same idea. When I was saying before, we built an ansatz, a circuit class, and then we have a classical algorithm find the best solution within those boundaries. That exact statement applies to machine learning as well. It's exactly the same concept. You build a neural network architecture, and then your optimization algorithm searches within that architecture for the best machine learning model for your particular problem. And also in machine learning, a decade or up to this point probably, very little is known why a neural network is well suited to recommend the next book that I want to read, right? Or the next movie to watch, or help a drone navigate around obstacles. Yeah. So the interesting thing, though, from which we can learn in the quantum computing community, is that the machine learning community has fully leaned into that ambiguity in this heuristic mindset, what I sometimes call adoption-led innovation, right? Where you build heuristic approaches, you build them and you test them, and you iterate with designs and that are driven by your intuition, and either they work or they don't work. Yeah. I read somewhere this analogy that I really like, where people say that working in machine learning today is a little bit like being an architect in an ancient society that hasn't developed the science of static yet, right? So you start building bridges and they fall down, and then somebody comes up and invents a pillar, and then the pillars are all the rage, and everybody builds pillars, and we still don't know if there's this hanging bridge out there somewhere that could allow us to build much bigger bridges. I mean, that's obviously a little bit provocative, but there's some truth to it. And for better or for worse, quantum computing will have to follow this mindset, this adoption-led innovation, in the near term, while we are in this NISQ era, where all the algorithms that we know are based on heuristics, right? On the same heuristics that helped machine learning thrive. Obviously, there are also other insights from machine learning that can help us, that can supercharge near-term quantum computing, and we're going to go a little bit deeper into that. But obviously, differentiable programming, optimization strategies that really pave the way for the success of neural networks, and the maturity of the end-user libraries that make it easy and intuitive to build and train and experiment neural networks and machine learning models were also crucial. Excuse me. So I actually want to look into that a little bit more, right? So what can we learn? And as I said, machine learning underwent a very similar evolution. When you think back of the 50s, when the first perceptrons were developed, the focus was very much on the computational complexity of these models of computation, right? So there was no general purpose hardware available to run the first, what we would today call a feed-forward network. In fact, the first perceptron, as far as I know, was run on a special purpose hardware that was built just for that, to prove that idea. And like in quantum computing today, it's very hard to prove anything theoretical about the computational power of these models, which I guess you all are familiar with this concept of the AI winters. So that led the field to become a little bit dormant until the 80s, when people rediscovered the backpropagation algorithm, which allowed for the first time people to build deeper networks, right? So there's this famous work from Jan LeCun about convolutional networks. That was, I think, one of the first works that showed that you can train deep neural networks using backpropagation. But even that wasn't enough, right, to bring really a widespread adoption of deep learning models. I mean, we can debate where this point on the right, which is labeled with deep learning revolution, where that point should exactly lie. But for sake of argument, from this idea of using backpropagation for training deep learning models until widespread industry adoptions, there were 2 decades, right, or more. So what was missing, right, and what did need to happen for this revolution to take place? So I'd argue there are three big pillars that led to that revolution. On the one hand, hardware and data became widely available and easily accessible for everybody. Open source tooling, right? So yes, backpropagation was there, but open source tooling emerged in the 2000s that helped make backpropagation, which is quite complicated, easy and intuitive and accessible. Well, and then, the machine learning was taken out of the lab and was brought into industry, into a whole set of different use cases. And while in the 80s and before, deep learning was mostly focused on speech recognition, vision, and when industry took this technology, the use cases changed, right? Recommendation engines and all of the other ideas became more prevalent. And without sounding too grandiose, but in a sense, that's what we're trying to achieve with Amazon Braket and with PennyLane, right? Amazon Braket, the goal is to bring on-demand access to quantum computing hardware to everybody and with no upfront commitment. And we want to integrate it deeply into AWS, because AWS is where our customers have their data, where our customers have their computational problems already available. And so, that was one of the thoughts behind Amazon Braket. The open source tooling, obviously PennyLane, we're super excited about this library because it brings ML tooling and differentiable programming to quantum computing. It is community driven and open to everybody. And then the third aspect, we do want to take quantum computing out of the lab and connect it to different domains and domain expertise from our customers. And importantly also, we want to bridge the gap between machine learning and quantum computing. Yeah, and that last point I want to look a little bit deeper into, because that is an aspect that's very near to my heart in a sense, right? As Rafal mentioned at the beginning, I have an education in quantum computing or quantum information theory, did my PhD and postdoc in the field, and then left and worked for several years in machine learning, and now are coming back to this field. And I have to say, I've seen both sides of the aisle. I've been part of both communities, and I've been super impressed by both communities in different ways. Yeah. So on the machine learning side, I really admire. I'm very impressed by the kind of builder attitude of people there. This driven mindset of just building and trying, be willing to fail and try again. And on the quantum computing side, obviously, many of the smartest people I've met in my life are working in quantum computing, and I continue to be impressed by the scientific breakthroughs that are coming out every day from this community. So the other thing that makes us really excited about PennyLane is that it is a bridge to connect these two communities, right? On the one hand, making quantum computing accessible for people out of machine learning or with a machine learning background, because they can just continue to use the tooling that they're already familiar with, like TensorFlow, etc. And on the other hand, providing the quantum computing community with the mature tooling, with the whole ecosystem around machine learning that has been developed, and we think that it's going to be beneficial. Both communities can learn from each other, and also from a service side within Amazon Braket. Like we're very closely aligned with our counterparts on the machine learning side, where have a joint vision there, and we want to bridge that gap because we believe there is a lot of synergies in these two worlds. So I mentioned there's a lot we're very excited about on PennyLane, and I'm happy to share again today that early in this week we announced that we are going to join the steering council for the PennyLane open source project. And we want to continue to evolve PennyLane as an open and community-driven project. We've worked with our friends from Xanadu to come up with a governance model that has, seats for community members on the steering council, as well as ways to encourage more community engagement, more community contributions. And this event here is a great testament to all the progress that PennyLane has already done, and we want to continue to build on that. So it's super exciting. Of course, we think Amazon Braket is the best place to run PennyLane, and we've worked with the Xanadu team, the PennyLane team, excuse me, over the past year to integrate PennyLane with Amazon Braket SDK. So you can get started quickly. It comes pre-configured on Amazon Braket notebooks. We have tutorials, and we have spent quite a bit of time to optimize the performance on Amazon Braket simulators, and I'm going to tell you a little bit about that as well. So, as you know, in variational algorithms, you have to execute many circuits at every step. Yeah, and with Amazon Braket and the integration that we have achieved with PennyLane, you can simply send these batches of circuits to our API, and Amazon Braket will take care of parallelizing this out and scaling this out into the AWS cloud. Yeah, so it's completely hands-off for you. And yet you can run these tens or hundreds of circuits in parallel through our simulator. And obviously that gives a strong performance improvement for training these algorithms against simulators. As you can see, it's very intuitive that the more you can parallelize that, the more runtime you can shave off of your workflow. So with that, I wanted to shift gears and talk a little bit about the hackathon next week. Excuse me, sorry, something in my throat. Looking at the hackathon next week, and talk a little bit about what we have planned. So today, we're going to the top 80 teams in the leaderboard who receive $250 in credits. We're going to provide instructions how to get started with AWS, and we recommend you in the first part of this hackathon to use our simulators because they're the most cost-effective way to prototype, to build your initial solution. Then on Wednesday, the top 20 teams will each receive $4,000 in AWS credits that you can use to showcase your solutions on simulators or on our QPUs. And then on Friday, we'll have the final submission due, and then the grand prize from the QHack committee. So before we get started, I wanted to tell you a little bit about best practices also. We have a question that comes up quite a bit is how do I use the different simulators? What are the differences, right? So we have 3 different types of simulators within Amazon Braket. This is a local simulator that comes built into the Amazon Braket SDK, most suited for rapid prototyping and debugging. You can run it locally on your instance or your laptop. So it's really, just out of the box, it works and runs quickly for smaller circuits. Then we have our managed simulators. That is SV1, which is a state vector simulator. It's kind of the generalist managed simulator. It is, fully parallelizable, like we discussed before. Typically, we say starting 20 qubits is what you would use it for. It has predictable runtimes. And then we have TN1, which is our tensor network simulator. So it's more specialized for special types of circuits. Of course, also parallelized and most used for circuits that have a specific structure. And I'm going to go into more detail what I mean with that. Because the runtime is a little bit uncertain with tensor network, it depends on how we analyze the network under the hood. We recommend to first try the circuits on TN1 with a few shots to understand how long it will take in general to contract the circuit, and then run it after that. So there's this uncertainty in TN1, how long will it take? And it depends on the hardness of the circuit, on the structure of the circuit. So what really makes it hard for TN1 to simulate a circuit? Well, it turns out it's actually entanglement itself that makes it hard to simulate a circuit for TN1. And if you think about it in that frame, it becomes very clear what types of circuits typically work well with TN1. Because if a circuit has a certain structure that slows down the spread of entanglement, like for example, local gates or sparse circuits, it becomes much easier to simulate. So for example, if we have only local gates, it's going to take a while for entanglement to spread from the first to the last qubit. So this is a circuit that would be much easier to simulate for TN1. And TN1 functions that it first looks at the structure of the circuit, it detects it, and exploits that circuit structure in the next stage when it tries to actually compute the simulation. And well, what are circuits with structure? I can give you two examples here. So there's, for example, the simplified 2 design layer or the basic entangling layer. And if those sound familiar, the reason is these are PennyLane templates, right? So you can use them out of the box, for example, and test them out with TN1. So here you see an example, right? So this is a quantum Fourier transform. It's interesting as a toy example where the pink line shows our state vector simulator. You see an exponential increase of runtime, whereas TN1 recognizes the structure in this circuit and is able to essentially simulate that with a flat scaling. So when we look at QPUs, also a couple of tips and tricks. So again, our QPUs are available on demand. We have a shot-based pricing, so make sure to check out the pricing page to understand what you want to run. When you use PennyLane, make sure that you understand the number of tasks that a certain algorithm will run and that you have an idea of what it will cost to run that. We generally recommend to first test and debug on simulators before accessing QPUs. Obviously, that's more cost effective. And then also, we recommend to use asynchronous execution on QPUs, right? Because they're not always available. We have our availability windows, but there may be some time that you have to wait in a queue before you can access the device. So we want to always asynchronously evaluating these tasks. So what does that mean? I'm going to show you a simple example. So this shows you how to, how to run a circuit. You would just do device.run. And then if you do .result at the end as well with multiple circuits, so it would send the circuit, wait for the result, send the next one, wait for the result. So that's not very efficient. You can do much better by doing it asynchronously, right? So you send first all the circuits, and then you, once all of these circuits are passed off, you collect them in one by one. Or even better, you can just use our run batch function that makes it a lot easier to send groups of circuits, and that's what happens under the hood when you run with PennyLane automatically without you doing anything. So with that, obviously AWS is like a big Lego box. We always say there's a lot of individual modules, individual parts, and it can be overwhelming at first, but people build very cool things, obviously, with the building blocks that we provide. But if you run into issues, if you're get stuck, don't wait. Get in touch with us. We're here to help. We have a global team of specialists available in the Slack channels that you see here on the right-hand side. We have another session about best practices that will start on Monday, 10 a.m. Eastern time from Pavel Legowski. And in general, reach out, get in touch. We're here to help, and we're super excited to see what you're going to come up with and what you're going to build. And with that, thank you so much for listening in, and I'm very curious to hear what questions you have.
Thank you so much for the presentation. Ooh, I'm just getting a little bit of feedback. Thank you so much. That was great. It's great to see how far along Braket has come in such a short time since its launch. Amazing to see all these great products added. You definitely have people excited. Maybe one of your early slides got people really excited, which was the applications of quantum computers. So one of our early questions is from Sammy Lives, who says, fundamentally, when can we use Braket to start solving logistics business problems? So maybe just a broader comment on your vision and AWS's vision on when we'll see that change in quantum computing.
Yeah, if I could answer that question, I probably would probably win a jackpot somewhere in one way or the other. I think the honest answer is I don't know. I don't think anybody really knows. Having error-corrected large-scale devices will definitely take a while. But that is the big technology frontier that we want to address with the AWS Center for Quantum Computing. And the question is, what can we do in the meantime, right? So we're going to have devices very soon that can do something that goes beyond what classical computers can do. And the whole idea behind variational algorithms is to see, can we harness the ideas of machine learning to find applicability for these new ideas, and how they could solve business relevant questions. I think the next 3 to 5 years, 10 years are going to be super interesting when we have devices readily available where we can test out these ideas for the first time without just doing it on paper or on simulators. I don't think anybody will be able to tell you this is going to solve a problem in 3 years or in 5 years. I think we have to be in this builder mindset and just build the devices and try it out.
That's an awesome answer. So maybe following up on that, you definitely focused on, in the near term, we have these variational quantum algorithms, and definitely people have ideas of what to do them in the short term. What do you think the future holds for variational algorithms once a fault-tolerant quantum computer arrives? Are they out the window, or?
No, I don't think so, right? Because we already know more or less that there are, for example, certain data sets where it's much beneficial to use a quantum computing representation, right? We know for a fact quantum computers will have a bigger, more representational power compared to classical machine learning if you have a certain type of data set, right? So that is, I think, very likely that we will see some kind of variational approach, and if nothing else, then in the context of machine learning. But again, only when we have fault-tolerant devices. I don't know. If we talk about optimization, if we talk about say computational chemistry, we will have to see. Obviously, we have other ways to address this. But if you look also what is happening today in computational chemistry outside of quantum computing, like these two approaches meld together, right? Like people are using machine learning for computational chemistry. They use traditional DFT algorithms for computational chemistry, and there are also a lot of interesting synergy in that field. Yeah, so where you have the kind of a priori algorithms still today deliver the best accuracy on your computational chemistry problems. Machine learning models have the advantage of having a much higher throughput, right? So there is an argument to be made that maybe variational algorithms have just different characteristics, but will continue to have use cases down in the future, even if we have fault-tolerant quantum computing.
Awesome. So a couple more questions from the audience that are coming in. There's been a few around. How do you, as AWS, partner with researchers? Is there programs or credits that they can go after?
Yeah, I mean, for us, it's extremely important, right, to recognize that this technology is not just an engineering challenge, right? So we all know this is very academic. There are lots of technological, scientific, open questions. And so we want to make sure that we're very connected to the academic community. On a broader scale, obviously, the Center for Quantum Computing, that is one of the mission statements. We have, researchers that are leading that centers, but we also have what we call the Amazon Scholar program. So we have a way for people from academia to join this effort. For example, we have John Braskell is an Amazon Scholar, is just called one. David Schuster, Yang, and others that help us out, but is a way for us to stay in touch with academic research, right? So this is one program. In terms of credits for for academic research, yes, we are providing, there's a program called AWS Credits for Research. We have a specific process there for quantum computing. And so we're always eager to see what people want to do with Amazon Braket specifically and how we can support that research. So I'm happy to drop the link to that program after this talk in the chat.
Awesome. I mean, maybe just a small extension. I believe your few people have already been dropping it from the moderating team.
Okay.
So they're directing people on the right side. But there was a follow-up question to maybe that, which is also for partners. I guess you have a premier partner program for ML and DevOps, and people are interested if similar things exist for Braket and Quantum as well.
Yeah, you see, I mean, our partners on AWS are super important, right? It's the force multiplier for us. We pay a lot of attention to make partners successful on AWS, generally speaking. In ML, DevOps, and the more established areas, these are really scaling actions where we have proven patterns that we know how we enable startups. In quantum computing, we're doing it on a much smaller scale, and there's a lot more hand-holding and kind of customized support. So while we don't have the formal track that we have on machine learning, right? So it's a machine learning specialist partner, for example, we don't have that formal track, but that is not an oversight. That is a conscious decision because we don't think we're in scaling mode just yet in quantum computing, and we want to be much more custom, much more with an open eye on learning ourselves what partners need in this stage and in this industry. Build on. We want customers. We want partners to build on Braket. This is one of our themes for 21, and we want to enable startups and software developers to build their applications on Braket. And please reach out. We are always eager to learn what you guys want to do and how we can support it most effectively.
All right, awesome. So no official program, but your DMs are open. There's his Twitter handle, so feel free.
I should say there is no official program, right? So we have a team that is working on startups, that is working on quantum computing specifically in that space. But we don't have that scaling program, right? Where it's like all templatized and we know what to do and we know what exactly happens at every stage of the way. It is much more custom, more hand-holding in our space at this point.
Yeah, also based on who's on your AWS Scholar list right now, I'm becoming suspicious that you recruit exclusively from Quantum Twitter.
Yeah.
A certain number of
Yeah, exactly.
There was also a request for a bit of a history lesson. I'm not sure. I know Nathan did provide some resources for this, but you made a few comments on kind of the history of backpropagation. I'm not sure whether you have that in your head and you want to share a bit of what that was like, but there was some interest in hearing that.
Yeah, I mean, now I'm getting on thin ice, but I know that, for example, the breakthrough of backpropagation with neural networks happened in the 80s, right? And shortly after this, Jan LeCun's doctoral thesis where he developed the convolutional nets, right? I think that maybe 2-3 years before that, so mid 80s, I would say. But interestingly, that was not the development of backpropagation, right? So that algorithm existed since I'm not gonna lie, but since the 60s, 70s or something like that, at least a significant time before mid 80s. And it was kind of rediscovered and applied in the context of neural networks. And that was really one of the technological breakthroughs in the 80s that really made it possible to for the first time, train networks that are, a little bit deeper, right? I think everything before that was essentially what we call like a, 3-layer feed-forward network. And then the combination of backpropagation with neural networks allowed you to go to more sophisticated architecture like convolutional nets, and especially to deeper networks.
Awesome. Back to AWS products. There's a question around your tensor network simulator TN1, and it's really focused on: is there any plans to open source that core tech? And then, or even possibly, it'd be great to see some benchmarks compared to the other efforts that are out there.
Yeah, in terms of open sourcing, we work with a lot of different open source libraries, first and foremost PennyLane, but also other efforts out of academia. And we like a lot of the things that are being built by the community. I cannot comment on kind of service implementations. We don't have a plan yet to specially open source, the secret sauce in the service. But there are a lot of, super interesting tensor network related libraries, from QIMP to PastaQ and others that we're watching very closely and are closely aligned and working with, with the folks that are building these libraries.
Awesome. I'm pretty sure you have a personal fan in the chat based on some of the questions that are coming in. I can't read this question directly. I don't think it's appropriate for air. But the gist of it is, do you run a Minecraft server?
Do I run a Minecraft server?
Correct.
I do not. No. I wish I did, but no.
Yeah, I have a feeling that you're going to have to jump into the chat afterwards just to clear up some of these things on your own.
Okay. I'm curious. Now I'm curious.
Yeah, I mean, maybe to just kind of shift away from the technical pieces, you have a pretty unique journey in terms of how you ended up actually at AWS doing quantum. So just curious what caused you to leave away from academia originally and move away from the quantum space, and then what brought you back?
Yeah. So I think for me, the point when I made the decision that I wanted to do something else, it wasn't a decision against academia, right? I mean, quantum computing, quantum physics was always kind of the thing that excited me from very young years on. But I was running a little bit into a timescale problem, right? The topics that I was working on during my postdoc, it felt like we were very far ahead of experiment, right? That's a general problem in quantum computing, I think. And you come up with an idea, and then it takes several years until somebody tries it out in an experiment, and then it takes another 10 years until it's potentially commercialized at some point. And for me, I really wanted to work on something that has a more direct impact. Yeah, and I started looking into machine learning in the context of my research at the time, and got super interested in the field. And kind of realized that there are lots of opportunities, and all the skills that we have developed in quantum computing over the years are very, very, very relevant in machine learning. And many people have that journey from STEM fields, from physics into machine learning, and it was kind of a natural transition for me. Then. Yeah, I had several positions in machine learning, and I really loved it. And most recently, I was running our global specialty practice in ML on the East Coast here in the US. And I think there was really only one job that could have come along that would have triggered me to leave that, because I really love that job. And that was something with quantum computing, right? I always joked with my boss at the time, say, if you hear anything about quantum computing at AWS, it's going to happen at some point, right? And so if you hear anything, let me know. And then, and actually, it happened to be that Misha Lukin, my advisor during my postdoc, he actually called me up and said, "Hey, have you heard that Simone Severini has joined AWS?" I said no, and I looked him up then in our corporate directory and got in touch with Simone, and was de facto the first hire in the quantum computing team at the time. I helped out unofficially at first, and then at some point, I had to make a decision: do I really want to flip over into quantum? And was a really exciting opportunity to start something like that at AWS, and I wanted to be part of that. But that was pretty much the only thing that could have happened that would have led me to leave machine learning.
How do you think that journey has actually influenced your viewpoint on the current state of quantum computing?
I think that it gives you a good dose of realism. I think when you've worked in machine learning on customer projects, and you see where where even machine learning is on the adoption curve, right? For many customers, this is still a very emerging technology, and I think there will be a reckoning, specifically when you think about quantum machine learning in our community, when we start thinking about the actual operational challenges, right? This is kind of a topic that seems kind of too far out to even talk about, but I'm getting the shivers thinking about deploying a quantum machine learning model in production, right? How would you even do inference when the device drifts away underneath you and you have to retrain based on your calibration data? And there are so many operational challenges that we rightfully so don't have on the radar just yet. But I think there's still a lot of hurdles to take until we will see just operational adoption of quantum computing.
Awesome. I think there's still more questions coming in, but I wanted to shift away from those and do something a little bit different. We put out this meme contest at the beginning of the announced hackathon. So people have been submitting a whole bunch of different memes. There's a whole bunch that we're not allowed to have actually within the actual competition because they come from our employees, our friends. So we can give it out. But I wanted to get some of your opinions on these. So here's the first one. I think it's a pretty classic template. What is your first impression? Is this a good attempt or not so much?
I think it's pretty solid, right? I like it. Yeah.
Yeah, to me, this one was one of the classics. I think that one was from originally, I want to say Juan Miguel, but I might be wrong.
Yeah, that is awesome. I was joking, for me, sometimes these demonstrations also feel like the people that play Doom on their Casio wristwatch or try to get Doom to run anyway. that feels it the same way, kind of with hydrogen molecules, VQE simulations at the moment as well.
Are you allowed to comment, even though it's not Jeff Bezos holding the racket here?
Yeah, no comment.
All right. And I think we have one. This one is personal to me, so I'd like your opinion on it.
Yeah. Look, I think this is actually rings true very much, because you could also draw the other way around, right? The elephant body with the penguin hat, and I think that cuts very close to me, right? Because I actually am not a big fan of the term quantum machine learning, because you talk to 5 people and 5 people will tell you they understand something different under that term, right? From just meaning the application of variational principle to quantum computing, or using quantum computers to do machine learning, or using machine learning models to build better quantum computers, right? So there's so many facets of that the word quantum machine learning doesn't do it justice. I don't know the good solution to it, but I'm always very weary to use the word quantum machine learning, because you speak to the wrong people. It's just being hyped because it's 2 emerging technologies being together. and we have to be very careful to make sure that everybody is on the same page what you're talking about, actually.
Yeah, I always like the qualifiers too, because it depends on what you mean. Do you mean like we're doing variational quantum algorithms and that brand of quantum machine learning?
Right.
Are we doing the idea that some people that I'm going to say are maybe a little bit too early for this approach, but trying to accelerate classical machine learning methods with quantum compute? Or then there's the whole third branch as well, which is classical machine learning for controlling quantum systems, which we're seeing a lot of now in both the academic and industrial settings. So I sat on a lot of random talks now where quantum machine learning gets brought up, and you have 3 different people talking about 3 completely different topips.
Exactly my point. I think that's what makes that term so dangerous.
Well, what would you call it instead? Well, let's recoin the field completely. You have the power to do it right now. What are you going to call it?
I was when I was putting the slides together, I was thinking, should I put quantum machine learning on that slide to explain this kind of variational quantum algorithm labeling? And I decided against it. And I said I call it learning quantum machines, which is just jumbling the words around, but it was just to avoid that confusion. So I don't have a good answer to that, honestly. But
there is a learning quantum machine out there from a different company, and it's really a very different thing. Yeah.
Oh wow! I had no idea.
I'll send you some links.
Copyright infringement. I have to be careful.
I was going to say one thing. We kind of ask all our speakers beforehand to give us some fun facts about them, And the one that you put forward is the fact that you can literally set any room on fire with your karaoke skills.
Well, that one has a backstory, though. You want to hear that?
I would love to hear it.
So you have not been to our AWS offices in New York, but we're literally right at the border to Koreatown. So it's very natural for us to go, do happy hour and go karaoke. And so we had some kind of there were phases where we had like bi-weekly karaoke appearances, and on one night I indeed was singing with somebody else, and I did send the speaker on fire. So we were just singing, and the speaker caught on fire in the room, and in Koreatown we were like on the 5th floor, and everything full of smoke. We were running out, and I remember we had an intern at the time from Germany. It was like this 20-year-old kid, and he ran out on the floor. He got the fire extinguisher, was trying to run back. I said, "Are you out of your mind? Get out of here! We're in Koreatown. Let's run." So yeah, I mean, positive, right? We didn't have to pay our drinks, but still, my clothes smelled like smoke.
Awesome. We were planning on queuing up the Frozen soundtrack for you to sing to, but given that I think you're coming down with maybe a little bit of a cold, we'll spare you.
Thank you. Yeah, I have a little bit of a throat issue going on, so I appreciate that.
No problem.
That's the only reason. Otherwise, I would have blown you away.
You know what? We already are planning another quantum music session for next year's QHack. But what we'll do is we'll have you come in to provide the vocals for that song. So we'll get it all set up with Eduardo. It'll be perfect. Eric, thank you so much. It was great having you on. We're looking forward to the rest of the hackathon and the challenge. So we'll see what the great teams come up with. And I'm sure we'll talk soon. Have a good one.
Thank you so much.